Performance parameters. In this session, we describe a number of op-amps design parameters, providing an understanding of why and where each may become important. For this discussion, here you can see the figure cascode op-amp. Consider the differential cascode circuit shown in figure as a representative op-amp design. The voltages VB1 minus VB3 are generated by the current mirror techniques described in chapter. In the open loop gain of an op-amp determines the precision of the feedback system employing the op-amp. As mentioned before, the required gain may vary by 4 orders of magnitude according to the application. Trading with such parameters as speed and output voltage swings, the minimum requirement gain must therefore be known. As explained in chapter, a high open loop gain may also be necessary to suppress nonlinearity. It is instructive to compare the circuit of figure with an open loop implementation such as in figure. While it is possible to obtain a nominal gain of GMRD is equals to 10 by a common source stage, it is extremely difficult to guarantee an error less than 1%. The variations in the mobility and gate oxide thickness of the transistor and the value of the transistor typically yield an error greater than 20%. Here you can see the figure simple common source stage. Small signal bandwidth. The high frequency behavior of op-amps plays a critical role in many applications. For example, the frequency of operation increases, the open loop gain begins to drop. Figure. Creating large errors in the feedback system. The small signal bandwidth is usually defined as the unit gain frequency FU, which estimates 1 GHz in. Here you can see the figure a gain roll-off with frequency. Today's CMOS op-amps, the 3 dB frequency F3 dB may also be specified to allow easier prediction of the closed loop frequency response. The key point in the above example is that the required bandwidth depends on both the settling accuracy and the closed loop gain that must be provided. Large signal bandwidth. In many of today's applications, op-amps must operate with large transient signals. Under these conditions, nonlinear phenomena make it difficult to characterize the speed by merely small signal properties such as the open loop response shown in figure. As an example, suppose the feedback circuit of figure incorporates a realistic op-amp that is with finite output impedance while driving a large load capacitance. How does the circuit behave if we apply a 1 volt step at the input? Since the output voltage cannot change instantaneously, the voltage difference sensed by the op-amp itself at t less than or equal to 0 is equal to 1 volt. Such a large difference momentarily drives the op-amp into a nonlinear region of operation. Otherwise, with an open loop gain of say 1000, the op-amp would produce 1000 volts at the output. As explained in session, the large signal behavior is usually quite complex, mandating careful limitations. Output swing. Most systems employing op-amps require large voltage swings to accommodate a wide range of signal amplitudes. For example, a high quality microphone that senses the music produced by the orchestra may generate instantaneous voltages that vary by more than 4 orders of magnitude, demanding that subsequent amplifiers and and filters handle large swings and or achieve a low noise. The speed for large output swings has made fully differential op-amps quite popular. Similar to the circuits described in chapter, such op-amps generate complementary outputs roughly doubling the average swing. Nonetheless, as mentioned in chapter and explained later in this chapter, the maximum voltage swing states with the with device size and bias currents and hence speed. Achieving large swings in the principal challenge in today's op-amp design. Linearity. Open loop op-amps suffer from substantial non-linearity. In the circuit of figure, for example, the input pair M1 minus M2 exhibits a non-linear relationship between its differential drain current and output voltage as explained in chapter. The issue of non-linearity is tackled by two approaches: using fully differential implementation to suppress even order harmonics and allowing sufficient open loop gain such that the closed loop feedback system achieves adequate linearity. It is interesting to note that in many feedback circuits the linearity requirement rather than the gain error requirement governs the choice of the open loop gain. In the noise and offset, the input noise and offset of op-amps determine the minimum signal level that can be processed with reasonable quantity. In a typical op-amp topology, several devices contribute noise and offset, necessitating large dimensions or bias currents. For examples, in the circuit of figure, M1 minus M2 and M7 minus M8 contribute the most. We should also recognize a trade-off between noise and output swing. For a given bias current, the overdrive voltage of M7 and M8 in figure is lower to allow larger swings at the output. Their transconductance increases and so does their drain noise current. Supply rejection. Op-amps are often employed in mixed signal systems and sometimes connected to noisy digital supply lines. Thus, the performance of op-amps in the presence of supply noise, especially as noise frequency increases, is quite important. For this reason, fully differential topologies are preferred. Thank you.